Next, before the break, we have Catherine Blundell of Oxford, who's going to give us a talk on the jets in the galactic microquasar SS433.
Good morning. Well, I would like to join Tony in adding my thanks to the organisers of this meeting, most particularly Preeti and Dharam and Prajval and Ishwara. Thank you so very much. Well, this should be playing a movie. There we go. This is now playing a movie, which is designed to be a cartoon of what the galactic microquasar SS433 would look like if we could observe it each day, every day, for 163 days, and if we could color code the material moving towards us blue and color code the material moving away from us red. Unfortunately, because other people have wonderful things they want to do with the VLA, it's only possible to get one night at a time, but I hope that you recognize that this zigzag curly corkscrew structure strongly resembles sequences from the previous movie. In fact, this corresponds to day 65 of the movie that I just showed you. Now, the picture to have in mind here of what's happening is that matter is launched ballistically from near the black hole at the very center of all of this. The matter is launched in two directions, anti-parallel to one another, along an axis which precesses, tracing out a cone every 163 days, resembling the paddle of a kayakist in the rest frame of the kayak. And the semi-angle of that precession cone is about 20 degrees, something like that. Some folk find it a little easier to think in terms of this picture, which is actually more physically accurate, where you're launching pairs of bolids, pairs of cannonballs in anti-parallel directions, along directions which themselves precess with time. So I made the comment yesterday that it could be rather amusing to play with these precession models. And so I want to show you a version of the movie now where I'm fixing the precession phase, but the parameter that I'm now changing is the launch speed of the jet material. So initially at very low speeds, this is the speed here, the appearance of such an oppositely directed jet system is really very symmetrical. I should say I'm also changing the parameter of distance, but that's purely to preserve the angular size on the screen. Otherwise, we'll end up in Andhra Pradesh otherwise as this thing shoots off the screen. So we're scaling the angular size, but speed is fundamentally the quantity that we're changing. And these asymmetries get really very pronounced indeed as the speeds approach the speed of light. The reason being that this blue material coming towards us is a long way out of the plane of the sky, and the red material is a long way back the far side of the plane of the sky, as it were. And we'll have had to leave in order for, we receive light at a constant telescope time, as it were, from all across the source. The light that's come from the stuff that's way back beyond the plane of the sky needs much more light travel time, and so what we actually observe left the object much earlier in time, at a much earlier epoch, so it's less evolved in some sense. But I hope you agree, about quarter C is roughly what corresponds to the image of SS433 that I showed you. Now again, following on from the discussion we had yesterday, I do just want to make a brief extragalactic interlude on the subject of precession. We had the comment about, can you apply precession model to extragalactic sources? Well, Katrin Steenbrugger and I did just that, noticing that you can't fit a straight line to the jet in Cygnus A. But it turns out, if you take the Jelming and Johnston model, you can absolutely fit a curly-whirly line to those, in which case the precession parameters, forget 20 degrees, the precession cone is 1.4 degrees, the precession timescale is 1,000,000 years, not 163 days. And the speeds, the best fit speed is actually about 0.35 C, and speeds faster than 0.5 C don't fit. So it is interesting to just play around with these. So it's inevitable, of course, that precession in extragalactic objects is going to be on much longer timescales than in the microquasars. And of course, we really struggle to get temporal resolution for quasars. But there's a way of doing it. If we bring in the X-rays, we can apply a kind of spectral binocular vision, which I'm doing here with 3C294, which is at redshift 2. This is over 100 kiloparsecs. The contours here are radio emission. That's the jet axis shown very clearly. But the color scale here, this arises from X-ray inverse Compton scattering off the CMB. Now, X-ray ICCMB lobes live way longer than radiosynchrotron. Sorry, this is just to remind us of the beautiful data that BG presented yesterday on 4C35.06. And to really say that I do think there's a lot of interest in this, but just to pick up on the comment about X-ray ICCMB being longer lived than radiosynchrotron lobes, this is work done with Philip Mox and Andy Fabian. This is luminosity on this axis, time on this axis. The dashed curve is radiosynchrotron. We switch the jets off after 10 to the 8 years, and the intensity plummets. On the other hand, the solid line is the X-ray ICCMB. That increases as you boost up the number of gamma 1000 electrons that can then upscatter CMB photons. And indeed, you can see that this is way more long-lived. And so you might expect that if you look at radio-quiet quasars, that if you can't see, that it might be quite fruitful to look in the X-rays to see if you can find them. And here is an example. This is about 490 kiloparsecs end to end. We only see lobes in this object at X-rays. We search pretty deeply using the GMRT. Absolutely nothing there, although it's a very nice fidelity map. And because I made a promise to Gopal Krishna, I will return to how this applies to the radio quietness of quasars in a subsequent extragalactic interlude. But back to precession as observed in the nearby microquasar SS433. If you overlay day 65 from this movie on the data that I showed you, this is the same image but colored green instead of blue, one's initial thought is that this is a rather good fit. But actually, as you play, as you explore, move the transfer function around, you do actually become a little bit less satisfied. At least you do when you've applied a Sobel operator to the image, which is a mathematical function that just delineates the ridgeline of the jet quite clearly so we can see which way it's going and where it's doing. And then you can see that actually it's not such a good fit, because here it's as though the plasma has moved more slowly than the model here. Here it's as though the actual plasma has moved more quickly than the model here. So to try and get a handle on what these different speeds were doing, we just allowed ourselves one free parameter. We fired out bolids on the computer, fixing the precession phase and the launch angle and all the rest of it, and asked the question, what do I need to vary the speed by in order to land in the ridgeline? So of course you do that. And then we said, well, how do those faster and slower speeds, when fitted to the east side of the object, work in the context of the west side of the jet? And the answer is that you do get a really pretty good fit. It's as though these velocity variations always want to be symmetric. And we've done subsequent studies of symmetry, which really do seem to be borne out. If you histogram up the speed variations in the 15 months captured by just that single VLA image, then we easily span from 0.2 to beyond 0.3 of C. So clearly one can get a lot of information from just one resolved radio interferometric image, be it from the VLBA as here, the VLA here, the GMRT, or whichever. But it's actually also extremely enriching and instructive to do optical spectroscopy on the very nucleus of this object. Do optical spectroscopy and try and learn about the line of sight speeds that you see in contrast with the transverse analogues that you see in the radio. And this is the kind of optical spectrum that you see when you point at SS433. There are various stationary lines, the most important one of which is the stationary Balmer H alpha line. Blue shifted jet lines, red shifted jet lines. what actually happens as the launch axis changes and precesses with time, then as you become closer to the plane of the sky, these red shifting and blue shifting lines move around and cross over, as I'll show you with some data now. This was from the ESO NTT telescope observed just a few years ago, and I hope you can see that those are getting rather closer. So close to the plane of the sky here, at the start of that little sequence, we were as close to the line of sight as we get. Now, it's been known for donkey's years that the SS433 jet axis precesses with, in recent times, this precession period of about 163 days. You can see there is quite a lot of scatter on this fit, and it's been very instructive to study that. Now, the solid line that I just showed you, showing those oscillations on the previous slide, is actually described by the kinematic model, which of course is very closely related to the Gelming and Johnson model, which also deals with the proper motions. Z plus here is the red shift, Z blue is the blue shift. Z plus goes together with these plus signs, the blue shift goes together with these minus signs. So we've got two equations. This is called the kinematic model. We've got two equations, and if we perform the following simple trick known as addition, then we can completely eliminate the angular terms here and get something. We take the simultaneously measured red shift and blue shift, and we just get something that depends on the Lorentz factor corresponding to the speed with which the bolids are launched. And you can trivially rearrange that to think in terms of beta. You can do an analogous trick, differencing the equations, dividing out the beta-gamma dependence to get something that purely depends on the angle. Now, launch speed and launch angle are famously degenerate in astronomy. We're always having to deal with beta cos theta. Not so when you can measure the simultaneously measured blue shift and red shift in the context of a symmetric precessing model. So mindful that one could really do all sorts of things with this, one of the many things I did, which I don't have time to go into, was just to difference the actual observed speed variations with respect to the kinematic model, and you can see that there are indeed speed variations which are at exactly the same RMS as what we inferred from that single radio image. If one now looks at the angles, then you see something interesting. This too is variable, but when that goes down and up and down, that goes up and down and up. And in fact, down here and then up here and then. These two quantities, the speed and the angle, are strongly, strongly anti-correlated, and that seems very robust. Yet, when we separately Fourier transform the angle data and the speed data, so the launch angle and the speed at which the bolids are launched, you see a great big spike at 163 days. That tells you your Fourier transform code works. You see periodicities corresponding to the nutation, which is superimposed on the precession in this system, which I haven't had time to go into. And the speed knows nothing about that. So we're convinced that these are two very, very good and very, very useful physical quantities. But the prospect of being able to play with the knowledge of the real-time launch speeds and the real-time angles led me to instigate a project called Global Jet Watch, which is designed to try and study how matter gets spat out at these speeds from nearby black holes. So it seemed to me the ideal way of doing it is the expensive route would be a dedicated satellite. The cheaper route was simply to put a bunch of telescopes separated in longitude around the planet. So you've always got one of them in darkness, which of course is a requirement for optical astronomy. So I've put telescopes in South Africa, Chile, Pacific Ocean is a bit of a hindrance, Australia right, Australia left, and here in Karnataka. And that's just terrific in terms of being able to study both with fine time sampling, the sort of things we want to do. We generate these things called our availability plots or our 24-hour night plots. And each of these curves corresponds to the air mass from one of those 5 observatories, giving us continuity of coverage in a way that just is not possible with a monolongitude observatory. This is one of those telescopes. The diameter is 0.5 meter. Just to help you calibrate here, much of the early work done on SS433, contributing to that 1984 plot I showed of Margans, were taken with telescopes with just 12 inches in diameter. This is the top end of the telescope in Chile. This is the inside of one of the spectrographs, beautifully designed, highly efficient, high-throughput spectrographs designed by my colleague Steve Lee at AAO. I won't go into the telemetry. The Global Jet Watch team is very lean. This is me installing some of our meteorological equipment in South Africa. My postdoc in Oxford, Sam Doolin, who's done much of the pipeline for the reduction of our spectroscopy data, and Steve Lee, whom I just mentioned, who designed the spectrographs. And my gratitude to these organizations is absolutely profound for getting us started. And you know what? Optics works. We get out beautiful optical spectra. So we have a treasure trove of fantastic and rich information. You probably recognize here the stationary Balmer H alpha line, helium, helium. That's another helium line. Blue shifted lines here, red shifted lines here. Relative to the H alpha line, the intensities of the jet lines vary really quite significantly. I'm just zooming in here so you can see a little bit more clearly. We measure the blue shift and the red shift. On this particular occasion, the speed was 2.4. On this particular occasion, you can see the relative intensities of the jets was rather higher. The speed was 0.26. And on this occasion, let me just add, that's a helium line. The blue shifted jet is this one. The speed that we get is 0.27 C. But if you've got eyes attuned to see optical spectra, you may notice that these lines are rather fatter than the ones in the first spectrum that I showed you, and coming together at a time when the jet speed is ramping up, in fact, is because a flare is imminent and on its way. But I'm just going to zoom in now to this bit of the spectrum, just showing stationary hydrogen, stationary helium, and stationary helium. And you can see that we're getting on for 100 angstroms spread in these various lines. In comparison with, I'm now going to show you a corresponding zoom of the very first spectrum that I showed you. These guys are rather narrow, more like 70 angstroms and so on. And what's actually happening with the onset of a flare is that in the optical, you suddenly... Surely not. Really? In the onset of a flare, accretion-disk lines appear, blue-shifted one and red-shifted one, and those themselves speed up just before the launch of a flare. This is the radio data associated with the flare I just drew your attention to, and this is an X-ray point from MAXI, which seems to herald the actual moment of launch of the jets. Whenever we have a jet flare, the speed increases sometimes to above 0.3, but I can honestly make this strong statement. For every single flare that I've looked at, the jet speeds are really very enhanced. And in fact, in this particular paper, which was the first flare paper, there's a Gantt chart describing the different processes that happen with the accretion disk and the jet lines. Now, I don't have time to discuss this in detail, but this, in fact, is the sequence of VLBA images made by Amy Mirdajewski, which my grad student, Rob Jeffrey, is analysing. He's looking at the fluxes and the proper motions of all these points. And we're finding, with the VLBA radio data, the same story that we've seen in the optical, namely that slower speeds seem to go together with being faster, and higher speeds go together with more intense, presumably more massive objects. And there are some subtleties I don't have time to go into about how the light curves of those individual bolids behave. Turns out that depending on the succession timescale between successive ejection of jet bolids, you'll get them colliding into one another. We can measure the expansion speeds fairly well. I'm sorry I don't have time to go through this carefully, but we're measuring the expansion speeds both from the optical and the radio and getting an answer that's a few % of C. I'm closer to the end than you might think, but I'm taking a detour into the microquasar Cygnus X3, which in its flaring event in 1997, the launch speed was 0.81 C. The precession period fitted to its model was 30 days, and the cone angle was just 5 degrees. In contrast with a flare just 4 days later, studied by my then student James Miller-Jones, jet speed as fitted independently by successive multi-epoch proper motion measurements and by this rather funky precession model you see here to have a jet speed of 0.67 c, a precession period of 5.5 days, almost a factor of 6 lower than how it behaved 4 years ago, and a precession cone angle 3 times bigger. Now, this is the same object, but obviously the spin and the mass are not going to change, but the jet speed can change and the precession characteristics can change. Let me just briefly mention that the duty cycle of jet flaring in Cygnus X3 is twiddles a week in, twiddles a year. And I think that in my last minute, I just want to bring this to bear against the discussion of radio loud and radio quietness that we've had of quasars. Now, jets are switched on for at most 10 to the 9 years. We're going to get slightly better limits, I think, on that presently because of people who are doing really important work, Ishwara and his students, Pratik and Madhuri. They're going to get us really good limits on how long can jets switch on for beyond this sort of twiddles 10 to the 9 years that we notionally know at present. But what happens when that jet switches off? I showed you the light curves that Philip Mox and the rest of us calculated. When you turn the jet off, the light curve absolutely plummets. And so our suggestion is, and similarly Steve Rawlings and I did quite a bit of work, all based on physical arguments that because of the expansion losses, the radio lobes must absolutely fade and disappear on very short timescales. Carlo Nipoti, James Binney and I explored the duty cycle of a whole bunch of different microquasars in their flaring mode, by which we mean their jet ejecting mode, and we commented on the important similarity between their duty cycle and the fraction of quasars that are radio loud. And our conclusion was that radio loudness is crucially a function of epoch, and most certainly not something like spin, because otherwise, you know, how does Cygnus X3 fit into that kind of picture? Consistent with this is the behavior of the double doubles, which give us some handle on the duty cycle in the extragalactic quasars, of course. So this is my final slide. I didn't mention earlier, but SS433 is actually embedded in the W50 nebula, which is going headfirst into the galactic plane. The galactic plane is around here. That's why it's a bit foreshortened this time. And SS433 fits into that stationary dot, unlike the unsteady green dot that I'm holding. Centered on that dot, by which I mean not quite centered on that dot, there's actually been a bit of proper motion there as well, due to a natal kick from the supernova explosion. This is impressively circular and is almost certainly what gave rise to the black hole at the center of this object. Yes, we've known for years that jets are launched from SS433's black hole nearby it at about a quarter of the speed of light, but we're uncovering lots of new things about how those jet speeds vary, how they dramatically increase, and what's the associated behavior with the accretion-disk and other modes of mass loss. And I'll stop there. Thank you.
Questions?
One of the things which I think is very important with SS433, which you didn't stress quite so much, is the symmetry of the ejection. Because this is something we take for granted in other objects. We assume that jets are intrinsically symmetrical, but this is one of the very few cases where you actually test this. So my question is, firstly, what are the constraints on the emission of two blobs emitted at the same time? Are they, emitting identical amounts of radiation in the rest frame? And secondly, are there any other objects, any other microquasars where there are similar constraints?
To answer the first question first, obviously since the study that I did mention where we looked at jet variation on each side, which gave us the first clue that there was some quite startling symmetry in this object, it's something we've had our eyes open for very much. Now in the optical, it's actually a little bit hard because there's a bit more attenuation in the blue than in the red. not just from the interstellar stuff towards the galactic center, but in addition, something that I didn't get time to mention, but you can see here in this VLBA image, is this rough, which is going approximately sideways with respect to the jet axis. Now, we think that is actually fed by a circumbinary disk of hydrogen-emitting matter, which we see perfectly clearly in the optical, but it's pretty, and the other important point to mention about this is that it too precesses across the plane of the sky, swinging by about 67 degrees. So there are times when that rough really obscures and attenuates the optical jet lines in the way that you don't think, but in a way that seems consistent with the orientation of the rough. So I think we get a more helpful handle on this by looking at the radio VLBA, and in looking at the images that were taken by Amy Mieczewski, the sort of 40-odd montage that I showed very briefly. My student Rob Jeffrey is looking at those, and that does seem quite impressively consistent. You never get sort of a fast blob on its own, and then just a sort of slow meandering one. They seem jolly, jolly consistent with symmetry in mass and in launch speed. Are there other microquasars where we can do this? The answer to that question, I would say, is not yet, not very easily, because one of the unusual things about SS433, I mean, it's jumping into flares the whole time. Not the whole time, often. We've seen two big flares during 2015. There was a massive one last year in 2014. But in many other microquasars, such as Cygnus X3, you do have this period of quiescence where presumably there's ongoing accretion, presumably there's still mass loss via its accretion-disk wind, but those are not terribly, that doesn't make for a very efficient use of time, because typically by the time it's gone flare, you've missed the very activity we want to study. But I have both schemes and aspirations to find some more microquasars with which to do this kind of analysis and extend the generality of the symmetry that does seem to apply in this case.
Hi, I know you didn't have time to really go through all the other data that are available for us for the in particular the X-ray data, because one important thing that we found in the X-ray data was that the correlation of the speed, the apparent correlation of the speed or anti-correlation of the speed and the angle could be better explained by changes in the jet direction on one side versus the other side on time scales that are probably a bit smaller than you would normally be sensitive to. Perhaps perhaps these differences last longer than the half day or so longer than we observed in the X-ray.
That's not something we've been able to see replicated in any of the optical data, of which we have quite a lot now. So I wouldn't presume to criticize X-ray spectroscopy, because I know it's a black belt art, but I find myself wondering whether here it's very clear when you've got moving hydrogen lines, when you've got moving helium lines. We see those very clearly, but I wonder if there's scope for how confident you can be that you've disambiguated the various different ion lines absolutely correctly. I wonder if that's quite...
Oh, the lines are very clear and they move very clearly. But the main difference is that you're looking at blobs after they've been traveling for of order a day. Okay, they're a light day out, actually, as opposed to the X-ray flux, which has to occur at very small distances because of the cooling timescales are much shorter in the X-ray band. So I believe that we're looking at a phenomenon which, in the X-ray, which is much closer to the origin of the jets.
Yeah, that's all true. My comment was about line identification and how confident one can be.
Oh, yeah, that's good.
We've looked at some of the other Chandra data again, and we're getting a slightly different conclusion.
Well, I'd like to talk to you about that then, because I'm pretty sure about the line IDs.
How do you constrain the inclination angle of the jet?
In the context of a processing jet model?
Yeah.
It's one of the parameters in the model. So the ingredients of the Jelling and Johnson precession model are ballistic motion, symmetric launch, and and then there are just parameters like the speed with which you launch, the precession angle, the inclination of the axis of symmetry of that precession cone to the line of sight, and the distance of the object from us. So in SS433, we actually know the distance to within 0.2 kiloparsecs. In the case of extragalactic jets, then you hopefully know the redshift, as Mohammed is going to be talking to us more about precession later. But in the case of 4035.06, that BG described to us yesterday, I think the redshift is known, so I'll be eagerly on the lookout for what that tells us.
Okay, I just wanted to comment on your little digression talking about possible precession in the extragalactic sources. The sorts of simulations that Sasha and others have done show the end of the jet sort of wiggling around just as a consequence of the way it propagates out without any real precession at the base. So I am not surprised that you could fit reasonable precession models to some of the shapes of the jets that we see, which is kind of like a snapshot in some of these simulations. But I'd be a little bit hesitant to try to interpret these as precession, because I suspect that they could be fit by other models as well.
Well, you'll notice that my slide said precession model fits to Cygnus A. I didn't actually say Cygnus A is precessing. Yeah. But I think in the case of 3C294, which was on my next slide, where you've gone like that in the X-rays to that in the radio, that's clearly not a wiggling dentist drill type phenomenon.
Yeah, with changes in jet direction, we see lots of changes in jet direction, for example, on the VLBI scales. But again,
that was over 100 kiloparsecs, the one I showed.
Okay, but again, if you've got two snapshots, essentially, it's hard to...
I absolutely wouldn't wish to claim that the extragalactic world is where we get the best time resolution.
The implications would be so profound that I think we'd have to be very, very careful about.
Well, I think this makes it all the more interesting to hear from Biju about his precession model fits to 4035.06. And we'll hear from Mohammed later about Hydra A, I think. We'll hear from him about precession as well, so that'll be interesting.
I think you wanted to... Sorry.
Yeah?
Okay, yeah, oh yeah, yes.
Yeah, see for the extreme relativistic case, what you're showing the relativistic simulation, right? For the animation was there.
So sorry, I couldn't...
Can I see the animation that what you are showing for the precision jet for relativistic case? So the animation you are showing, no? The jet animation.
The cartoon?
Yeah. Can I see that once?
You'd like to see it again?
Yeah. For the relativistic case, the next one, the second one, for the relativistic case.
That one?
No, jet speed.
Oh, thank you. That one.
Right. Here I can see the one question I have is, why at the nozzle, the jet is not precessing at all? Means, is it I'm not...
I know it's not precessing at all. I think it's something to do with this. There we go. Sorry.
Yeah. See, what I can see is around the edges of the jet, you can see the nice precision. But at the nozzle, we are not actually seeing any precision. Is it a relativistic effect or?
No. It's just that the phase is fixed. In this simulation, I'm not changing the precession phase. The only parameter I'm really changing is the speed. I'm actually changing the distance as well, but that's just a scaling function, so it still fits on the slide.
So one more question I have is, for example, if I extend it to the extragalactic jets, so there we have the Doppler factors are very high compared to one. So in that case, what happened? Your blue shift and the red shift. So if actually the jet is precessing, I may be wrong. What I'm saying is I will see a dots, bright dots when it's comes towards me. Am I right? And the other side will be dim. But do we see that patterns in the extragalactic jets? It may appear as a spiral, but when I see that, since it is moving towards me, I see dots, and the other side will be dims.
I've not seen a crystal clear example from the extragalactic land. That's not to say they're not out there, and indeed Eileen and I were discussing some possible objects that, just for the sake of playing with the data and poking with it to see what's in there, it's certainly a fruitful thing to play around with.
You could look at M87, actually, the outer part of the jet, like not A, B, it has some hints, especially in the proper motions data, that something is rotating possibly. And the knots are still open to interpretation. I think
Is this elongation of W50, has it been observationally detectable?
I'm sorry, I didn't.
Elongation of supernova, W50,
Yes.
elongation,
Yes.
has observationally been detectable over last 30 years?
The expansion of the supernova. Not yet, but we've taken successive multi-epoch observations of the W50 nebula now span a few decades.
Yeah.
And so we published a paper on the limits with data from the first 20 years in 2011 or 2010, I forget. My student Paul Goodall and we were looking for evidence of the proper motion. But optical spectroscopy on the supernova remnant shell does give you the expansion speed. We did do a simulation of the W50 nebula, and we reckon the age was about 20,000 years. I think the simulation allowed between 17,000 and 21,000 years since the supernova exploded.
Okay, I think last question.
So when this cannonball is launched, so why do you expect that there will be only, for example, if there is asymmetric kick to the cannonball, there will be rotation in the cannonball also. So, and if the rotating cannonball is propagating through the ISM, it will deviate, and then you will expect, you are overestimating or underestimating the radius of these spiral things.
The reason why I think that's not happening to a great extent, certainly not to a measurable extent, is because the supernova remnant that we were just discussing, or rather the supernova, effectively acted like a spherical snowplow and really cleared the decks in terms of the matter that surrounds SS433. So it really is a relatively pristine environment for it to propagate out into. So I think we're fairly clear on that.
The kick to individual cannonball can be that it can rotate. So then if you image a group of the cannonballs, part of the jet, then you will see broadening type of thing because individuality is rotating, so blue shifting and red shifting.
We see expansion. We see a signature that we can explain by spherically symmetric expansion in the rest frame. We don't see a signature of rotation, which may be because the ISM density is just nice and clean and empty.
How can you tell this apart?
Sorry?
How can you tell the two apart?
Well, presumably if rotation, I'm sorry, I've forgotten your name. If rotation happens as is being suggested and the entrainment follows, then you'd start to see expansion that wasn't isotropic. It depends a little bit on the details of the ISM, but it's a very, very pristine environment for this jet to expand into.
Okay, I think it's time for our tea break. So let's thank Catherine again.